Okay, everyone, we only have a few people today, probably because of the time changes. I don't know, maybe people will join later. But anyway, we can start this session now, and then let's see how many people will join. Okay, so from today, for the next 4 weeks, we are going to cover more practical sessions on how to calculate um, solar photovoltaic potentials and wind potentials in selected country, selected area, more like selected area. And I selected Jeju Island in South Korea. And before we actually start doing the calculation, okay, start calculating the potential, I'm going to give you a little background today, and then we'll show you some example by Susop will show you some example on how to calculate the potential and how this result can be used, and also what kind of things that you need to consider when you calculate solar photovoltaic potential in South Korea. So let's just start our session now. Everyone can see this screen, right? I'm sharing this correctly, right? Okay, great. Thank you so much. So the title today is Renewable Energy Potential Calculation using QGIS. And today we are going to cover how basically basic understanding of um, wind and solar potential calculation process. Such a long subtitle, which can be slightly longer than the main title. But let's just start. This session is going to take about 30 minutes, I think, and then we will jump into Susok's session right away after about 10 minutes of break. So before we calculate the potential or to calculate potential, we need to understand what kind of solar photovoltaic we have, what is its technical features, and what kind of things or limitations that we need to understand. So we need to understand the technology. There are three different types of solar photovoltaic in general. Of course, um, if you classify them more in more details, then we can have many more like types, but usually I just consider them as three types. First, we have rooftop solar photovoltaic. Second, we have land-based or utility scale solar photovoltaic. And thirdly, we have floating solar photovoltaic. And in case rooftop solar photovoltaic, the biggest benefit is it doesn't actually need any land. So, and but the problem is you only have a very limited land, limited area. For example, as as the name or as the type of this solar photovoltaic says, you need roof, right? So in many cases, roof uh, roof area, total roof area of a country is pretty limited. For example, in case of South Korea has a huge population density, so that we have lots of high-rise buildings and apartment in urban area. So that unlike Australia or United States, total area where we can build rooftop solar photovoltaic is sort of limited, right? And also, there are some regulations that you need to consider. For example, if the building is illegal building or unregistered building, usually you are not allowed to install solar photovoltaic. And also, you need a certain standard. For example, the building needed to be fireproof, or need to be strong enough to hold the weight. So there are some rules that you need to obey. And you why do we need to use this rooftop solar photovoltaic with all this restriction? Because first, you don't need additional land area. That's the major benefit. Second, you don't need to pay electricity bill if you have solar photovoltaic. I mean, it's not like becoming zero, but you don't need to pay. You can reduce your electricity bill quite significantly using solar photovoltaic. The reason is quite interesting because usually people tends to use more electricity during daytime, right? And then solar photovoltaic generate electricity more during daytime so that the demand and the supply pattern matches well. So usually solar photovoltaic is quite useful to reduce your electricity bill. And the next one is land-based solar photovoltaic or land-based PV. I'm going to just say PV because photovoltaic is too long. So land-based one. Land-based PV is also called utility scale PV because in case of solar, in case of rooftop PV, its capacity can be, I don't know, up to 1 or 2 kilowatt maximum, depending on what kind of building you have actually. But in case of land-based or utility scale PV, the entire size or capacity can be go up to several megawatt. And if you have enough land area like United States or Australia, you can build a couple of 100 megawatt of solar PV as well. So that's the big benefit. However, the problem is you need to lease the land or you need to purchase the land. That makes the entire cost a bit higher than rooftop PV. But there is a catch because rooftop PV is small in terms of scale, right? However, land or utility scale PV is much larger than rooftop PV. So that when from the perspective of a developer or perspective of supplier, land-based PV, I mean, per kilowatt or per watt capex of land-based PV can be cheaper than rooftop PV, right? Because of the economy of scale. So that's kind of benefit. However, this is an example of South Korea. We have about 25 gigawatt of solar PV. Yeah, correct me if I'm wrong. To the best of my knowledge, it's about 25 gigawatt of solar PV. And there are people or there are developers who would like to build more solar PV in South Korea. However, there is a problem that there is not enough land area. When I say not enough land area, it doesn't mean physically limited, but financially, it is really difficult to find cheap or economically available land area in South Korea, so that the capacity increase is a little bit slowed down than before. And because of those issues, there are some other types of solar PV that people are trying. One is floating solar PV. This is, I would say this is very new concept, but a very rare concept. And I remember that when I was working for a research center in Singapore, there was a research group who focus mostly on this floating solar PV, because Singapore really doesn't have much land area to build solar PV. At the same time, what Singapore is trying is make the entire rooftop area green rather than black, so that having more solar PV, rooftop solar PV was not really an option. So that what they could try was having floating floating PV on their lake area, right? Same for South Korea. There are a couple of tries trying to use floating PV. However, the problem is, in case of floating PV, usually its efficiency is lower than the others because of the moisture. Moisture reduces those global horizontal irradiation to the panel, so that its entire efficiency can be a bit lower than before. And then it costs more when you need operation and management. So when you need to clean it, you can't just access. You need to go there by boat or something, and then you need to have some special equipment to make this entire solar panel float on the water. right? And when there is a flood or some issue with the water, it can be damaged as well. So there are some issues with floating. And then another one that I can think of is building integrated PV, or so-called BIPV, which is similar concept with rooftop solar PV. However, the difference is in case rooftop, it only uses the roof, right? But BIPV uses the wall of the building, so that you can install. So you can install this PV on the wall of the building. The thing is, compared to the roof, you can have much more area. However, because roof is flat, like um, horizontal to the ground, so that it's much easier to install. However, the wall is vertical, right? So you will not get enough enough irradiation from the sun, so the check efficiency is usually lower. And then another problem that you can think of is the reflection. Yeah, solar PV can reflect the sunshine to the ground or to the other building, which can cause bit trouble with sometimes it becomes legal trouble as well. So it can be a problematic. So those are the solar PV that you need to understand. But during our session, what we are going to focus is land-based solar PV, because rooftop and floatings are much easier than land-based solar PV in terms of QGIS calculation. So we need to go through two different steps to calculate the potential or PV potential. First, we need to understand the solar resource. So how much of a solar resource that do we have in a certain area? It can be a square meter or square kilometer area or something like that, or it can be a very strange looking area, whatever it is. The most important thing is you need to have a data. You need to have a proper solar irradiation data. Of course, there are ways that you can avoid using solar resource data. However, then in the end, it is not going to be very, how do I say, very accurate, right? And then the second thing that we need to do is we need to understand the suitable installation area. So how much of an area that we can use, right? So for the both calculation, we are going to use QGIS, and QGIS is mainly very useful when you calculate the suitable installation area. But also we can do the same calculation. We will use QGIS to do the solar resource assessment calculation as well. But technically for this solar resource assessment, you can do it only using Excel as well. So how do we choose a suitable area? What are suitable to build solar panel and what are not build solar panel? Can you write it on the comment, on the message? Which area we can't build in your country? Just think about your country and what kind of area that you need to avoid building solar panel. So there are a couple of examples. First, military base. Yeah, it's quite obvious. They wouldn't like it. I mean, it would be better if we actually don't have any military at all, but it's not practical in this real world because human is not really kind to everyone, unfortunately. So we need some sort of military. And in case of military area, building solar panel is not going to be very ideal because it can reveal where the military area is, and also it can make those military, how do I say, training sessions be more difficult or complex, right? And there are some other areas, for example, in case of rural area, you might want to avoid agricultural land area. However, there are some other issues. There are some other ways that you can use the agricultural area, which Susok will present later. And then urban area, in case of very urbanized area. Thank you so much, Hyunwoo. Definitely, you can build solar panel in parking area, but the problem is due to the shade, usually its efficiency is pretty low. So that's why many people really don't. developers don't like parking area unless there is a huge compensation from the government just because they built it. And also, so in case of suburban area, those are very good places where you can build solar panel, particularly the rooftop solar panel. And thank you, Seripa. Avoid agriculture and forest area. Yes, yeah, those are the things. Here is one wetland area. Usually, I would say usually, many wetland in around the world are registered as a Ramsar protection area or natural protection area as well. In that case, you can't really build it. And if you build solar panel, basically, you are killing the ecosystem. So yeah, reducing greenhouse gas emission is definitely really important. However, protecting our nature is as important as reducing our greenhouse gas emissions. So we need to avoid them. And then we have some like Amazon or more natural area, like where how do I say endangered species living, or the habitat of endangered species should be avoided as well. And then yes, mountain. That's very good point. I mean, not all mountains should be. I mean, it is very depends on where to put more value, but you can build solar PV in mountains. However, building solar PV on mountains costs a lot because it's not flat, and access to the mountains with all those equipment is not going to be really cheap, right? So mountain is usually avoided. And also because of the landslide, mountain with a certain above a certain slope is also avoided. In case of South Korea, the limitation was 25 degrees or something like that, and then reduced to became more strict to 15 degrees, so that any land area above 15 degrees of a slope are not allowed to build solar PV. And also, we have airport, right? You can't build solar PV in the airport because of this reflection. Usually, the reflection is the key in case of airport. And then, yeah, can you think of any other places where you can't build or you can build solar PV in your country, context of your town, or where you are sitting, or your country? Can you give us a couple more? Anyone? Let me ask this to Susok. What do you think? Any restricted area you can think of?
Agricultural promotion areas?
Yeah, that's one thing. Agricultural promotion area. There is a classification. I mean, land classification in South Korea. Agricultural promotion area is the places where the land must be used only for the agricultural activities, nothing else. You can't build anything else but just a farming. And I can think of the river. You can't build even floating PV on the river because it will float literally, right? People have attached the solar panels on the roof and of their mud houses. Well, I mean, as far as it works, it's fine, and mud is quite fireproof, basically. So seems it would work. As far as it can be managed well, that is going to be the key. So yeah, during this session, during the next 4 weeks, there are many approaches, or there are many techniques that we are going to use, but we are going to focus on the 3 operations mainly, so that you can get used to these operations. Those are basically the key operation of QGIS. You already did some GIS workshops during the last 4 weeks, and you might already knew that GIS calculation is basically same with the set calculation. So you have difference, you have interaction, and you have union, and you have clip, and etc. and etc. So, but those are three things that we are going to use: difference, interaction, and probably union. It depends on what kind of approach we use. So difference basically retains all area not overlapping, and intersection, as you know, retains only overlap zones or overlapped area. And union basically combines all area, right? Those are three things. Let's go back to solar photovoltaic technical, the technical specification of solar photovoltaic. I don't like this audio. This sounds better, right? Because, yeah, bear with me because English is not my first language at all. And yeah, sometimes I need to fix it. Yeah. So how does solar photovoltaic work? It's easy, right? Everyone understand that. Everyone can see that, right? There is a solar irradiation coming down from the sun. Basically, it's called the sunshine, right? And then we have some kind of black mirror look like panel, which is called solar photovoltaic or solar panel. And then somehow it observes this sunshine and then generate electricity. And we put those electricity into the inverter and then change those DC electricity to AC and then put it into the grid. Or you can directly use those DC to charge your phone or I don't know, in your camping site or something like that. But how does this solar PV actually work inside? If you see the inside, is basically semiconductor. Not too much different with semiconductor. So when it sunshines, it generates electricity basically. I mean, I just told exactly the same thing twice because I don't understand the entire system exactly. The main point that you need to remember is when the sunshine is converted into electricity, only 20% of the solar irradiation becomes electricity, right? Only 20% of sunshine can become the electricity. Yeah, that's basically the technical limit unless we have a big breakthrough using other material. But at the moment, the silicon-based PV cannot create more than 20%, cannot achieve more than 20%. Maybe can go up to 25% or something like that, but still around the 20%. And if there is a new type of solar PV, which is called the Febrovsky or something like that, yeah, very strange name. Anyway, if the material is used, the scientists says the efficiency can go up to 60%, which is basically the game changer of this climate change and solar PV industry as well. And then this is how it works. And then there are some issues with solar PV. First, when there is a shade, you lose some sunshine, right? So solar PV will generate less electricity. And when the panel is not clean enough, it will lose all the electricity. So in old days, there was a bit of a misunderstanding that if we install solar panel in Sahara, each electricity output is going to be huge. There was a bit of misunderstanding, but in practically, if you actually install solar panel in Sahara, or if you install the solar panel in Middle Eastern area, each output is not going to be too different with a solar panel in Germany. You know, Germany is not really a sunshine country, but even if there is a strong sunshine in Middle East, each output is not going to be too different. Why? Because the dust covers the solar panel, and then in the end, you have less electricity output from the panel. It's a very practical reason. And also temperature. When the temperature is too high, then solar panel doesn't work well. So we need a certain level of temperature control as well. That is another reason why it didn't work as expected in Middle Eastern countries. And then there are some conversion losses in inverter. And then also when you use solar panel, each lifespan is around 20 to 25%, 25 years. And every year you lose about 0.5 to 1.1% of each output every single year because it degrades. So in the end, after 20, 25 years, solar panel output is going to be about 75 to 80% compared to the initial stages, like battery. And then there are issues with weather, and also there are issues with a loss of a, um, I mean, curtailment as well. When there is too much solar panel output but not enough demand, you need to cut it out. Then you need to use those curtailed electricity, you need to use a battery, and battery costs a lot, much more than solar panel, so that electricity becomes more expensive and solar panel becomes less economically viable. That's what happens about the solar panel. And then there are, when we think about the solar panel, I just told you that several times that we need sunshine. The energy is coming from the sunshine. But what does this sunshine actually mean? It is irradiation. It is called irradiation. There are three different types of irradiation. One is global horizontal irradiation. And another is direct normal irradiation. And the third one is diffuse horizontal irradiation. Which one do we use? Usually, if you go to a database, you will have three different types of irradiation. Which one do we use? We use global horizontal irradiation almost always. Just remember that global horizontal irradiation. What are the difference? DNI is the irradiation directly from the sunshine, right? Directly from the sunshine. And then diffuse horizontal irradiation, DIF, is basically the irradiation which somehow reflected by the air or cloud or whatever, something in the end, in the air, rather than coming directly from the sun. Some of those irradiation can be reflected in the air and then came down to the land, right? That is diffuse horizontal irradiation, or also called DIF. And when we sum those DNI and DIF together, but using some strange mathematical calculation, basically cosine, we have global horizontal irradiation, which assumed the energy, this sunshine or irradiation is going to be just vertical to the land, right? That's GHI, global horizontal irradiation. So when you need to calculate solar potential, you can just use global horizontal irradiation. So what happened to this solar irradiation? The sunshine coming from the sun, obviously coming from the sun, and in the middle it scatters and it observed into the atmosphere and disappear a little. And then there are aerosols or water vapors in the air which can block or which can diffuse as well. And then major challenge is going to be cloud. Basically, when there is cloud, sunshine cannot really go through it, right? I mean, not 100%, maybe half of them, sometimes maybe 10% of them just blocks there. And then even after cloud, still we have a scattered observation, and then we have some other scattered, or we have some reflect due to flight and buildings and etc. etc. After all of this like reduction, we have the irradiation. And when the irradiation, when this global horizontal irradiation hit the land, this is the equation that we can how to calculate solar output. It's quite easy compared to the wind. Calculating solar irradiation is really easy. See, here is solar irradiation, which is global horizontal irradiation. Multiply it with the efficiency of the solar panel, which is 20%. Usually, if you just type it 20%, it is not going to be wrong. And then calculate with each total area. say in this case, if we are targeting, yeah, sorry about the singing because my understand that my washing machine just finished its job. So if we have 10 square meters of the area, then we can just multiply with 10. So when there is 5 kilowatt hours of a global horizontal irradiation, solar output is gonna be, what is that, 10, right? Is that correct? Yeah, I think so. 10 kilowatt hour per square meters. This is the solar output that we can expect. There is one thing that you need to remember. What is the size of this solar panel? In case of solar panel, it depends on the manufacturer's specification. However, usually one solar panel has about 150 watt per square meters of a capacity or capacity density or something like that. Right? This is basically the number you need to. There are a couple of numbers that you may want to remember. One is this, and another is this. This is not really important because it is going to be given by other data providers, but those two you might want to remember. Now, this is all about solar panel. Now, let's jump into the next next renewable energy source, which is wind. Compared to solar panel, wind is a bit different. I don't like this one as well. Wind turbine. So in case of solar panel, when there is sunshine, it basically creates or generates electricity, right? Quite easy. But in case of wind, how does it work? It is like windmill, right? When there is wind, it turns, and the physical or its rotator basically make the generator turn around, and then the generator create electricity using its magnetic field or something like that. But if you see wind turbine, actually you can see lots of times it doesn't rotate at all. It just stops. It happens a lot in South Korea. It really doesn't generate any electricity. Why? Because there is a cut-in speed and then there is a cut-out speed. This is simplified wind power turbine power output model, but not much different with actual curve. You can, if you want to see the real curve, you can go to Vestas website, and then if you type in their model number, then you can actually find this curve number. Let's try it together. We can go to Vestas wind turbine. Okay, see here. We can go to their website. The reason that I go to Vestas website is because their data is always quite comprehensive and easy to use. And here is one turbine that we can find. You can see it's called the V236 and 15 megawatt. That's a huge one. That's a pretty big one. And then there will be a manual somewhere. At least they provide some technical information here. Rotator diameter is 265 meters, as you can see here. And then its swept area is basically the total area that rotator is going to use. And then let's see what we have. And then its cut-in wind speed is 3. And then cut-out wind speed is 31 meter per second, which means when there is very strong wind due to like hurricane, wind turbine cannot actually generate electricity at all. If it's too strong, it needs to stop. And then the last one we will be able to see is gonna be a manual I don't think this website is gonna be provide any manual for us. Yeah, unfortunately not for this one, but yeah, you can find some manuals from other turbines. Then it will show you pretty much the same cut-in and cut-out speed, and then how this output curve works, which means between 3.5 meter per second and 14 meter per second, wind turbine will generate electricity in proportion to the wind speed following this graph. And then after 14 meter per second, when the wind speed is strong enough or fast enough, it can generate its full capacity up until 25 or 31, as we could see in the Vestas website. Then how can I calculate wind potential, right? If we think about the wind potential is very weird concept. Sometimes I find it very weird. In case of solar irradiation, each energy is coming from the sunshine. It is just there, right? But in case of wind, unless you specify the area where you want to capture the energy and specify the technical terms like, I mean, basically the technical terms, the radius and or sweep area, unless you define the sweep area, you can't calculate wind potential and wind energy. I mean, I don't know, maybe it's just me finding it weird because in case of solar irradiation, it doesn't matter if you have a solar panel or not, you can calculate irradiation. It's coming from the sun and each unit is kilowatt hour per square meter. However, in case of wind, if you don't know the sweep area, you can't actually calculate, you can't estimate the energy. That's a bit weird. Anyway, the way we calculate wind potential is basically this this equation. First, multiply 0.5 with wind density. Wind density is different by region. So when you download the wind speed data, you need to download wind density data as well. I'm going to show you where to find it. And then multiply it with wind speed. And it is basically v to the power of 3, which means wind speed is basically the key that decide its output. If wind speed increases a little, then each output is gonna be increased a lot, right? Because it's power to the 3. And then there is area, sweep area. That's the reason why those wind turbine developers want to make the blade longer, because area is R to the power of 2, which means if you have just a small amount of longer wind blade, then each output is gonna be increases to the power of 2, right? So it's basically the physics. This is the equation. There is nothing that you need to remember. Even I don't remember this equation exactly. So whenever I need to calculate, I just look up the website, look up the website like Vestas or somewhere and easy to find. Just remember that this wind power output is gonna be related to the sweep area and the wind speed and then wind density. Those three things are the key. There are a couple of places where you can find this data set. First place is Copernicus Climate Data Store. This is not really directly power or energy related data. However, you can find the temperature, wind speed, and humidity. But please remember, depending on your region, Copernicus climate data can be a bit underestimate the wind speed and humidity and temperature and things. You usually find with the temperature, but sometimes it has problem with wind speed. So that these days, people tend to use a renewable ninja, which provide hourly wind and solar pattern by country. But still, this doesn't really solve our problem because we need a solar and wind, basically solar irradiation and wind speed of each area. So there are two websites that I usually jump into, tap into, or jump into, whatever you like. One is Global Solar Atlas. Let's go to Global Solar Atlas. Global Solar Atlas is made by World Bank Group and ESMAP and Solar GIS, and this include quite useful data on solar irradiation and solar output and power potential and etc. of your country of interest or region of interest. Let's go somewhere. I don't know. Maybe try somewhere or Pakistan. As you can see here, in Pakistan, if you click on, you can find specific photo power output of this point, and then you can have direct normal irradiation, and we can find global horizontal irradiation. Yay, we have the data, right? I told you that we need GHI. Okay, we can see the GHI here, and then there is a DHI, and there are some other information as well, like air temperature as well. And you can calculate quite easily by choosing what kind of a solar PV you are going to install. And if you assume that if we have a ground-mounted large-scale solar PV, which has a 1 megawatt of installed capacity, then it will tell you that, yeah, at that point, you are going to have this amount of electricity per year. Easy. So this is what we have, but we can actually download the solar data from here. In this case, let's go for, I'm not sure if they have Singapore, but in many cases, Singapore is missed because the country is too small, maybe, I don't know. And there are some maps as well. And you can download basically global horizontal power output here as a format of GeoTIF. I'm going to provide this data to you, so you don't need to download it now. I'm just sharing the information of data. And then there is Global Wind Atlas. Basically, to the best of my knowledge, basically it's made by the same group. Probably, or maybe not. I don't know. I can't find. So global. This is the wind atlas. Let's go somewhere very interesting. I don't know. What about here? Maldives. In the middle of Indian Ocean. Here is Maldives or Maldives, and usually global wind atlas takes a little longer time than solar atlas. Maybe because it has more data set. I'm going to show you what kind of data set it actually has. First, as you can see here on your left side, it has a it looks beautiful. I really want to go there. Yeah, we have a wind speed, and then also we have power density, which is basically calculated output of wind speed, but we are not going to use it. We have wind speed, and then we have a bathymetry as well, which is the elevation of this area. And then there is a air density data as well, but I can't find it. Let me, source. Oh no, not this one. Yeah, there is a air density data, but as you could see in the equation here, let's go back. If there is no, sorry, not, yeah, wind density is basically the air density. we need air density or wind density data, but if you can't find wind or air density, you can just use the average, global average value, which is 1,200 or something like that. Forgot the, yeah, something like that, but forgot the exact number. The reason is because compared to the velocity or speed or the radius, wind density is not to the power of nothing. It's just power of one, right? To the power of one. And then each difference is less than 10% across the entire globe, right? So it really doesn't affect much. So you can just use the average. However, if you need to calculate very correct, accurate output, then you definitely need wind density. But this is going to be the data that I'm going to provide. So yeah, basically this is all about what kind of solar PV and wind we have and how to calculate it and technical background of calculating the potential. And then we are going to start calculate this potential from next week for the next 3 weeks, starting from next week. And then we are going to have about 10-minute break. And then when you come back on time, Susok Lee is going to explain you what kind of lessons that he got during his last work on estimating solar photovoltaic agrivoltaic potential in South Korea. This is going to be very interesting concept, particularly for those countries who based on agricultural land, agricultural industry a lot, like basically all Asian countries. This is going to be very interesting.